Let's show you how to use molality to calculate the molar mass of an unknown. A 1.25 gram sample of a non-electrolyte compound was dissolved in 75 grams of benzene. The solution froze 1.20 degrees C below that of the pure benzene. So that's your delta TF. Determine the molar mass of a compound if the Kf of benzene is 5.12 degrees C per molality. So we know delta TF is equal to Kf times molality times I. So if we rearrange this, we can solve for molality. Molality then is equal to your delta TF divided by your Kf times I, which in this case, since we're talking about a non-electrolyte compound, we know that I is equal to 1. We plug in our values. We're given delta TF is 1.20 degrees C. Our Kf is 5.12 degrees C per molality. Our degrees C's cancel. Our molality is in the denominator, which means it's in the numerator. So therefore, if we do our calculation, our final unit would be molality, and our final numeric value is 0.234. So the molality of this unknown non-electrolyte compound is 0.234 molality. Now, how is that going to get us to the molar mass? Well, we know that molality is your moles of solute per kilogram of solvent. Well, we can rearrange that moles to get to molar mass by changing the molality calculation, that ratio. We know moles per kilogram. We can take that moles and rewrite that in terms of grams of your solute per molar mass and then rearrange that equation. So knowing the relationship between moles and molar mass, we can rewrite molality. We know molality is moles of solute per kilogram of solvent. Well, we know that moles of solute is really your grams of solute per molar mass. Well, we know the grams of solute, we know the kilograms of solvent, and we know the molality. So all we can do is rearrange this and solve for molar mass. So rearranging, we see that grams of solute divided by our molality and kilograms of solvent will give us our molar mass. That'll give us the units of grams per mole. So plugging in our values, we got 1.25 grams of solute divided by the molality, which is 0.234 moles of solute per kilograms of solvent. And we plug in our kilograms of solvent, which was 75 grams, which we convert to kilograms, which is 0.0750 kilograms. You can see our units cancel, kilograms and kilograms. We're left with grams of solute per mole of solute, which are the units for molar mass, which when we multiply this out, we'll get 71.2 grams per mole is the molar mass of our non-electrolyte unknown. Homework 74. The last topic that we're going to cover, osmotic pressure. Osmosis is the process whereby a solvent passes from a dilute solution into a more concentrated one through a membrane permeable only to the solvent. The equalization of concentration between the two solutions in contact with one another across the membrane is what drives the process of osmosis. The osmotic pressure, symbolized by pi, is equal to the external pressure, P, just sufficient to prevent osmosis. Osmotic pressure is a colligative property and is directly proportional to the molar concentration of the solute by the following formula. Osmotic pressure is equal to your molarity times R times the temperature, where M is the molarity of the solute, R is the ideal gas constant, which is 0.0821 liter atmospheres per mole Kelvin, and temperature is absolute temperature, meaning the Kelvin scale.